Concavity and the second derivative test. Well, definition of concavity. Let f be differentiable on an open interval I. The graph of f is concave upward on I, the interval, when f prime is increasing on the interval, and concave downward on I when f prime is decreasing on the interval. So we look at this. There's the picture of what it looks like. The test for concavity, though, is working with the second derivative. So not just finding the first derivative, but you also have to find the second derivative. Third case of 3.7 could be that if f double prime of x equals 0 for all x in the interval, then f is linear. Note, however, that concavity is not defined for a line. In other words, a straight line is neither concave upward nor concave downward. The other key point up here is, notice if the second derivative is greater than 0 for that value, then it's concave upward. If the second derivative is negative, it's going to be concave down. Okay, example 1, determine the open intervals on which the graphs are concave upward or downward. We got two parts to this one. So first derivative of f of x, and I missed the derivative sign on that, so there should be a f prime right there. We get e to the negative x squared over 2 times negative 2 over 2 times x. That just simplifies to negative x, e to the negative x squared over 2. And then critical values would be 0. Second derivative, we take the product rule. So derivative of negative x is negative 1 times the second plus negative x times derivative of this, which we have right here. So I'm working smarter, not harder here. They both have an e to the negative x squared over 2. I'm going to pull that out. I actually pulled out a negative, and then that leaves a positive 1 here, and that's still going to be minus x squared because we pulled out one of those negatives. Critical values there are going to be plus or minus 1, and so we just need to test. So we're mainly concerned about where it's concave up or down, so we use the second derivative. So negative infinity to negative 1, negative 1 to 1, and 1 to infinity. And we're only concerned about the second derivative here because that's going to tell us our concavity. Plug in like negative 2, and we get a positive. At negative 1, we do get 0. Plug in 0, we get negative number. 1, we get 0. Plug in 2, we get positive. So that means for negative infinity to negative 1, that is concave up. Negative 1 to 1, it's concave down. 1 to infinity, it's concave up. So the intervals on which it is concave up is negative infinity to negative 1, and 1 to infinity, it's concave down on negative 1 to 1. On B, I got to do quotient rule. So derivative of the top is 2x. And then we multiply it by the denominator minus the top times the derivative of the bottom over the denominator squared. Do some simplifying, and the 2x cubes cancel, and that gets us negative 10x. Critical values for that would be 0 and plus or minus 2. Second derivative, derivative of the top is negative 10 times the bottom minus negative 10x times the derivative of the denominator, which is going to be 2 times x squared minus 4 times 2x because chain rule. But then I can make life a little simpler. Oh, and don't forget the bottom. We square that, so x squared minus 4 squared squared. On the tops, I can pull out an x squared minus 4 from both terms, and I can pull a negative 10 out of both terms. So I do that. That's going to leave just x squared minus 4 here. The negative 10's gone. I've got x times 2x, and that x squared minus 4 is gone. So it gets minus 4x squared. We can cancel an x squared minus 4 top and bottom. And then that top just simplifies to negative 3x squared minus 4. I can distribute times by a negative. We get that. And we've got our critical values from that. Well, it can't equal 0. So it's just negative 2 and positive 2 that we have to worry about. So just like the last one, I'm putting it in my table. Second derivative from negative infinity to negative 2 is positive. It's undefined at negative 2. It's negative from negative 2 to 2. so we would try plugging in 0. 2, it's undefined. 2 to infinity, it's going to be positive. Sorry for the interruption. And then it's concave up on 2 to infinity. So concave up, negative infinity to negative 2 and 2 to infinity. Concave down, negative 2 to 2. Definition of point of inflection. Let f be a function that is continuous on an open interval, and let c be a point in the interval. If the graph of f has a tangent line at this point, c f of c, then this point is a point of inflection of the graph of f. And that's just when the concavity changes from upward to downward. So we can take a look in between here. Here's an inflection point. Okay, concavity changes. And we can look at, here's our function, here's what its derivative looks like. And notice you've got it changes from positive to negative, that's an inflection point. And, well, actually that's concavity decreasing to increasing, so that's where the concavity is going to change. That's why it's an inflection point at this point. If f of c is a point of inflection of the graph of f, then either f double prime of c equals 0 or f double prime does not exist at x equals c. So, example 2, determine the points of inflection and discuss the concavity of the graph of f of x equals x to the 4th minus 4x to the 3rd. So I need the first and second derivative. First derivative is going to be 4x to the 3rd minus 12x squared. And that I can factor a 4x squared out of both, gets us 4x squared times x minus 3. Critical values are going to be 0 and 3. Take the second derivative, so 4 times 3 is 12, x squared, minus 24x. I can pull out a 12x from both of those, and we've got numbers to check for points of inflection of 0 and 2. So we put all of those numbers in a table, and we also discuss first derivative and second derivative, not just one or the other, and the function. So negative infinity to 0, 0 to 2, 2 to 3, 3 to infinity. And first derivative from negative infinity to 0 is negative. It's 0 at 0. 0 to 2 is negative. At 2, it's also negative. Notice right here, since 2 is a critical value for the second derivative, I just care what the sign is here for the first derivative. 2 to 3, it's negative. At 3, it's 0. And 3 to infinity, it's positive. Second derivative, it's positive from negative infinity to 0. It's 0 at 0. It's negative from 0 to 2. It's 0 at 2. 2 to 3, so like 2.5 is what we're plugging in. It's positive. At 3, it's positive because that's a critical value for the first derivative, not the second. And 3 to infinity, it's positive. Now, what does that say about the function? Well, right here, this says it's decreasing and concave up. Okay. That tells us a value of this, and if I plug in 0 for the function, I do get 0, so I'm just putting that there. Here it's decreasing and concave down. Sorry for that interruption. At 2, it is negative 16. When we plug it in, between 2 and 3, it's decreasing and concave up. At 3, it's negative 27. And on 3 to infinity, it's increasing and concave up. So what does that tell us? It tells us that we have changing concavity at 0, 0, and at 2, negative 16. So those are our points of inflection, 0, 0, and 2, negative 16. And we have a minimum because it's changing from decreasing to increasing at 3, negative 27. So the second derivative, it lets us know if a point's a relative min or max by just plugging that critical value into the second derivative. If we plug it into the second derivative and it's positive, then it's a relative min. If we plug it in and it's negative, it's a relative max. If f double prime of c equals 0, the test fails. It doesn't tell us if it's a min or a max. It could be either or neither. So last example is going through that process. So first derivative, negative 15x to the 4th plus 15x squared. Can pull out a negative 15x squared, which leaves us x squared minus 1. So our critical values are 0 plus or minus 1. Second derivative, negative 60x to the 3rd plus 30x. pull out a negative 30x, gets us negative 30x and then 2x squared minus 1. Our critical values are 0, and then what makes this 0 would be plus or minus square root of 2 over 2. We only need to check these in the second derivative. So f of 0 equals 0. F double prime of 0 equals 0. Second derivative test fails. Doesn't tell us if it's a relative min or max. F double prime of negative 1 is 30. That's greater than 0. That tells me that that's a relative minimum. And when we plug in negative 1 to the function, we get negative 2. And then f double prime of 1 equals negative 30. That's less than 0. That tells me it's a relative max at the point 1, 2.